So here we are in number 21. We have a hot metal coin dropped into cold water in a well-insulated container, so we can assume no energy exchange with the surroundings. Which statements are true? So for all the energy that leaves the metal and goes into the water, it will be the same in amount. And so we commonly say that as the heat of the metal is equal to the heat of the water. Really, it's just the heat transfer between the metal and the water. The absolute value sign there is because we traditionally write the Q of the one is equal to the negative Q of the other, as in one is gaining energy and one is losing energy, one is endothermic, one is exothermic. But statement here, number one, is correct because of that absolute value sign. Statement number two, on the other hand, talks about the entropy change. And entropy for this particular exchange is equivalent to your heat exchanged divided by the temperature of that substance. So the metal being at a higher temperature is going to be divided by a larger temperature. It's going to be a smaller entropy change, and that is the metal as entropy is going down, and then the entropy of the water is going up, but it's divided by a smaller temperature, so it's going to be different values. So this is not correct. And of course, the entropy of the water goes up more than the entropy of the metal goes down, and so our entropy of our universe, of course, is trending up. So if we look at our choices then, we're looking for one only, and that would be A there. Okay. So the second question, what's delta G naught formation of the gaseous form of the benzene here? So we're looking for this value. So in order to do that, we need to do kind of a couple things. First, we need to figure out for the reaction of the liquid form turning into the gaseous form. We need to figure out what the enthalpy for that reaction is, what the entropy for that reaction is, and then we're going to figure out the Gibbs free energy for that reaction, and we're going to use that to work backwards and find that missing value. So we're basically looking for delta G naught is equal to delta H naught minus T delta S. And we know that our delta H for this is going to be this minus this. Okay, our delta S is going to be this minus this, and our temperature is given at 298. So I have an enthalpy of 33.9, and that's in kilojoules per mole. Now I'm going to subtract from that 298, and the entropy change I have as 95.7. However, that's going to be given in joules per mole, not kilojoules. So I need to change that into kilojoules, and that comes out to be 0.0957 kilojoules. So when I do that arithmetic there, I end up with an Gibbs free energy for the reaction of plus 5.38 kilojoules per mole. Okay. And then what I want to do is I want to take that and say, okay, well the Gibbs free energy for the reaction is equal to the sum of the products minus the sum of the reactants. So it's equal to my missing value here, let's call that question mark, minus 124.3 kilojoules per mole. Well, I know that the Gibbs free energy of the reaction is 5.38. So something minus 124.3. So I'm looking at a case where this needs to be greater than this by 5.4. So we're looking at 129.7, which would be D. Okay, so a few steps in there, otherwise not too tricky. Okay, number 23 is not a tricky question, but it's kind of presented as one. So for this, if we look at graphite converting to diamond, okay, then our enthalpy for that reaction is going to be positive, so positive 2.1, and the entropy for that is going to be negative, which means that's never going to happen ever in a thermodynamically favorable manner. So this question asks, at what temperature will the diamond be in equilibrium? So in equilibrium is implying that we want a delta G value of 0, not a delta G naught value. And that's going to be equal to, assuming these are relatively constant, it's going to be equal to this value minus the temperature times this value. But both of those are positive values, and so that's not possible. So this is never going to reach an equilibrium. So if we look, we have three choices of temperatures, and then we have a fourth one that's not a temperature one. So probably our D is our answer. So now we need to check on this. It says graphite is more stable than diamond at all temperatures. So the way we've written this, we have a positive delta G at this point. So the delta G naught being positive means that this reaction is never going to proceed in the forward direction. And the implication then is that graphite is more stable than the diamond form. That matches our answer here, so we would go with D. Traditionally though, what we're looking for is we're looking for delta G is equal to delta H naught minus T delta S. We're going to solve for that temperature that makes delta G equal to 0. We can't do that in this case. It's not going to happen mathematically. Okay, so now we get into some of the calculation questions. Fortunately, I have a little help for this, kind of, if you know how to kind of configure this a little bit. So we have two equilibrium constants. It asks for delta H. So here's an important thing to note for this exam, is that this equation can give you guidance to a couple different equations. This is rate constants compared to activation energy, but that form of that equation is the exact same thing for equilibrium constants and enthalpy. Now, I write mine a little differently. They have K2 over K1, T1 minus T2. I write the opposite. I write K2 over K1, and then 1 over T2 minus 1 over T1, but I add a negative sign in there. So that's how I set that up. But you can keep that as is. It'll work out mathematically the exact same. But what we're looking for here is, I want the equation natural log of K2 over K1, and these are equilibrium constants, is equal to negative delta H over R. Okay, times 1 over T2 minus 1 over T1. So if you reverse these, that's going to be essentially creating the same number but opposite in direction. So that's going to cancel out the negative sign. So that's just how I write that. And then we can go ahead and plug in. So I want to keep K2 here as my unknown. So that is the equilibrium constant. I'm sorry, no, I know both equilibrium constants in this problem. So I'm looking at natural log, and let's go with the higher temperature first. It's the 42 degrees, so we have 7.8 times 10 to the negative 10 over the 9.5 times 10 to the negative 11. Okay, so that we're going to need to be careful plugging into our calculator. With some parentheses there. And that comes out to be 2.105. Then that's equal to negative delta H, which is what we're looking for. Over R, we're going to use 8.314. Now that's in joules, so this is going to come out in joules. And then we're looking at T2, so we need to match this 7.8 times 10 to the negative 10th with its temperature. So that's 42 degrees. So we got to make sure we put that into kelvins. So we're going to add 42 to 273, and that's going to come out to 315. And then we're subtracting from that 14 degrees, again in kelvins. So we're going to have 287. So from here we need to do this and multiply that over to the other side, or divide that to the over side, and then we're going to need to multiply 8.314 to the other side. So when we plug in everything, that comes out to be a delta H of 56,500 joules per mole. And here we have 57 kilojoules per mole, and so that would be our choice. Okay. Okay, this question I got wrong when I took the test. I made a simple mistake, but let's go into a little background really quick. Cyclopropane, okay, is going to be 3 carbons in a ring, and then propene is going to be a double bond and a single bond between 3 carbons. So this is C3H6. This is also C3H6. So when this talks about an isomerization, that's meaning that this changes into this with no additional chemical reagents necessary. So we have a 1-to-1 stoichiometric ratios, one of the important points on this. The thing that I missed is that I read that it was 22 millimeters of mercury of pressure to start, and then I read that this is what it was sometime later, but what I didn't read is that this is of the product. So we're starting with an initial of 22 millimeters of mercury of this, and then sometime later we have 17.5 millimeters of mercury of this. Well, we want to be tracking just this. So since it's a 1-to-1 ratio and the pressures are going to correlate to moles, what we can do then is we can just subtract those, and this comes out to be 4.5 millimeters of mercury of pressure when this is at 17.5 sometime later. So this is the value you need to use. Now from there, you can use this equation pretty easily. Oh, I'm sorry, this is not the right equation. So this is a first order case. This is something you would have to have memorized. So the equation for this traditionally is your final concentration is equal to your initial concentration times e to the minus kT. And that's for a first order reaction, which it tells you in the problem. For a second order or zero order, it'd be a different integrated rate law. But you should definitely know this equation. So we're just going to plug in 4.5 is equal to 22 e to the minus kt. Now, the time, it says 1 minute, but all of our constants here are in seconds. So I just put in 60 seconds instead of 1 minute. So I did 4.5 divided by 22. I did the natural log of that answer, and that's equal to negative 60k. I divided by negative 60. Okay, and when I did all of that, it came out to be, well, I know the answer is this. So 0.026, and B was my choice on that. Okay. If you do it with the 17.5, I believe it comes out to A, 3.8 times 10 to the minus third. And then, of course, if you move on quickly, you get it wrong. Whoops. Okay, 26, I'm not really sure what the deal with this is. This looks like kind of too simple of a question, too obvious, so I'm suspicious, but molecules must have correct spatial orientations for collisions. It's true. Only collisions with energy greater than a certain threshold, the activation energy, lead to reactions. That's true. Couldn't find anything tricky about it, so I went ahead and went with C, and that ended up being correct. So sometimes Chem Olympiad has easier questions. 27 is a really cool question. I like this one a lot. So we have two factors coming out here. They've plotted the concentration of triiodide ion versus time, and they've gotten a linear result. So that tells you something. That fact that this comes out to be a linear result means this is zero order with respect to the triiodide ion. Okay, if they had done natural log of this versus time, it would have been linear, it would have been first order. 1 over, and it would have been second order. The second thing they do is they tell you that they change the concentration of the acetone from 1 molar to 0.5 molar between these two. So if you look, we're starting at the same amount here, and it takes this long to get to a certain concentration of 0. So that's about 37 seconds. Well, this is about 74 seconds. So it's twice the time. That means this is half the rate, and this is half the rate and half the concentration. So for the acetone, when you double the concentration of the acetone, the rate goes up by 2. So we have some power here, doubling the concentration, where it causes the rate to go up by 2. So that means this is first order with respect to the acetone. So we can figure out the orders for both by doing these two experiments, okay? So then we look at our choices. We have first order, 0 and first order, that's our answer. First order and cannot be determined, first order and cannot be determined. No, we figured it out. So B is our answer, and that's a really nice question there. Okay, so this also is not too bad of a question if you kind of know what to do, or even if you just know what to do and don't really know what you're doing. But let's go through the whole thing. So our slow step is going to give us our rate law. So our rate is going to be proportional to each thing that's present in the slow rate determining step. So we're going to get rate is equal to K times the concentration of N2 times the concentration of O. But here's the problem with that. O is not present in our overall reaction. It's an intermediate only. Okay, you can see that it gets canceled out here and here. So as it gets generated, it later gets used up. So we don't want to write our rate law in terms of that. So we want to go back to the previous step. Well, in the previous step, this is at a fast and an equilibrium. And so O2 turning into 2 O's, what's happening here at equilibrium is the rate of the forward is equal to the rate of the reverse. So if we wrote out a rate law for the forward, the rate law of the forward would be some rate constant, let's call it K1, times O2. And the rate for the reverse would be equal to a different rate constant times O squared. Well, we want to get rid of the O. So what we can do is we can rearrange this and say that O is equal to the square root of K1 over K2 times O2 to the 1/2. Square root of that. Okay, so we can plug this whole thing in for O here. Now when we plug this in, we're plugging in a whole bunch of constants, but it's just adding onto a constant. So it's just going to be some constant. Now it's going to be different than this originally was. It's going to be multiplied by a factor of this. But we can plug all that in, and we can get a new final rate law. Where we get some, fourth rate constant times N2 times O2 to the 1/2 power. Okay, so that's our rate law, and then we go ahead and look, and that's our choice here in C, so C would be our response for that. Okay, so here we have an activation energy question. We're looking at two rate constants. I should have copied the equation on here. But the equation we're going to deal with here, natural log of K2 over K1 is equal to negative EA over R 1 over T2 minus 1 over T1, which again is backwards from the flip from what it says on the sheet. So we're just going to do a plug and check here. So we know our initial temperature and its rate constant. We know the activation energy, but we have to watch out for the kilojoules because this is going to be in joules. And we want to know the new rate constant. So I like to plug in the rate constant I'm looking for here. So I'm going to plug in natural log of K2, and then my initial rate constant is 0.032. Okay, that's equal to negative 41,000 over 8.314. Okay, and then K2 is the initial, or is the temperature we're looking for the, what is the rate constant at 410? So we want the 1 over 410 here to match that, okay? Minus 1 over 400. Okay, so we're going to figure out what this is, multiplied by this, divided by this, and let's see what we have figured out here. So, yeah, it looks like I just solved for the final thing here, but K2 ends up being 0.043, and that's C. So we'll go ahead and circle that. All right, and number 30, we have two substances, A and B. Rate is found to be proportional concentration of A at all studies, and at low concentrations of B, the rate is found to be proportional to B. So this is something that's basically saying, forget what you learned about kinetics, we have something weird going on, right? So we're basically saying, normally we're getting a rate law of Ka, but at really low concentrations, we're either getting, I'm not sure if I'm reading this correctly, I would say it's K times A times B at low concentrations. So you're getting two different rate laws. So you can't take what you learned in high school class and say, oh, okay, this is how you explain this. So we're looking for anything that could explain this particular oddity that we're observing. Okay, so part A says B binds to A prior to the rate determining step. So that does fit with our data because what that's saying is that in a previous elementary step, we have some interaction between B and A. So it's saying at really low concentrations, you're actually getting to the point where the kinetics of that fast step slow down enough to affect your rate. Does that make sense? So let's leave it for the time being. The reaction has an order of -1. That doesn't make any sense. So first of all, we're going to see a reaction order of -1, and then second of all, that doesn't correlate with what we're seeing here. It doesn't give us this nor this. So B is not correct. Reaction involves a 1 to 2 stoichiometry. So that also doesn't correlate with anything we're seeing here. And stoichiometry is going to have no bearing on your rate unless that's within the elementary step, which is not what's implied here. So C is also not correct. And then the reaction is catalyzed by one of its products. Well, that wouldn't make sense for the low concentrations of B all of a sudden changing things. And so between A and D there, I'm going to go with A as my better answer and circle that.